as Floriana just mentioned, I'll be talking about the significance and validation of the inter-period correlation on the simulations. First off, I'd like to acknowledge and thank Professor Norm Abrahamson, who's my PhD advisor at UC Davis, where most of this work was done. So the purpose of this talk is a little different than the previous ones, which were more large-scale frameworks for validations. And it's to really focus on one specific parameter that Floriana covered already, and that is the inter-period correlation of the ground motions, which we denote rho epsilon. So you'll see rho epsilon throughout the presentation. And so what I hope you'll take from this talk is that rho epsilon's a critical, trying to get rid of the video thing here. Okay, there we go. Now I can see. So rho epsilon's a critical feature of the ground motions that influences the variability of the structural response. And because of that, it should be considered as a validation parameter in earthquake simulations. And then I'll also show a few example validations and ongoing calibrations. So an outline of the talk, first an introduction, and then a little discussion on the significance of rho epsilon, how it impacts seismic risk. Ground motion modeling, what correlation do we observe in the recorded ground motions? And then compare that with what we see in existing simulations. And then there's sort of a iterative cycle of calibration of those simulations and then reevaluation of their inter-period correlation. Probably everyone listening here knows this, but physics-based earthquake simulations, in practice, they're going to be used increasingly in the next decades. But to use them, of course, they need to be validated that they contain ground motion properties found in the recordings. So everyone here knows that. A definition of epsilon. So epsilon is the number of standard deviations difference between the observed ground motion and the median model prediction in log units. So the equation is there. This figure from one of Jack Baker's papers a decade ago shows epsilon calculated for an individual record in blue at different periods. And so, for example, you could see epsilon at 1 second is 2.3 units. So it's 2.3 standard deviations above the median. So epsilon's a normalized residual, and epsilon is correlated between spectral periods. So what do I mean by that? If you were to calculate epsilon for an entire database, where each circle here is an individual recording in a database, and plot those epsilons up at 2 different periods or frequencies, in this case, 0.5 hertz or 0.2 hertz and 5 hertz, you could calculate the correlation coefficient between those. And so for these widely spaced frequencies, the correlation coefficient's pretty low. If you did the same thing for frequencies 0.2 and 0.3, the correlation's higher. So the correlation coefficient in this case is 0.74. And of course, if you were to look at the same frequency, well, everything's perfectly correlated with itself. So the correlation coefficient is 1 at 0.2 and 0.2. So this calculation can be repeated for each period or frequency pair of interest. And then these results are often presented in the form of contours like this. So in this figure, both the vertical and horizontal axes are frequencies, and then the colored contours are the modeled or calculated correlation coefficient. And so you can see it's 1 along the 1-to-1 line. And then another way to look at these is if you were to take cross sections of this figure. So I've taken cross sections where these 3 dashed lines are at 0.5, 2, and 5 hertz. And then in this figure, it's showing the correlation coefficient on the vertical axis and then the frequency on the horizontal axis for 3 conditioning frequencies. So as you can see, the correlation coefficient drops as you move away from the conditioning frequency. So that's what the inter-period correlation is. Why does it matter? So epsilon itself has been discussed before, is an indicator of the local peaks and troughs at a given frequency. And so the correlation coefficient between epsilons quantifies the relationship of epsilon values between periods, and it characterizes the relative widths of these extrema. So how broad are your peaks and troughs in a spectrum? Higher correlation means broader peaks. Here's two example Fourier amplitude spectra, one with lower correlation imposed. This is from SMSIM, and then one with higher correlation coefficients imposed. And so you can see that the one that has higher correlation has broader sort of undulating peaks and troughs. And I should mention this same concepts apply here to response spectra or to Fourier spectra. I kind of interchange between them. So as a measure of the width of peaks and troughs, the correlation is relevant in dynamic structural response. So this paper that I had with Norm, we drew these conclusions that structures are sensitive to a range of frequencies about the fundamental one, especially for nonlinear response. Therefore, the breadth of the spectral peaks influences the variability in the response. And so at the end of the day, we found that increased correlation leads to flatter fragility curves. And that's what I'm showing at the right here. The red line is calculated fragilities from simulations, incremental dynamic analysis in OpenSeas, where the simulations from the red, developed from the red, are have a higher interperiod correlation, and then blue is essentially uncorrelated. So there would be SMSIM or XSIM simulations. So the take home is that it influences seismic risk and is an important metric, therefore, for validation of simulations, because if you don't have any correlation between interperiod correlation, it might be unconservative risk estimates. So the models in the literature for the interperiod correlation, there's actually several of them. Here I'm showing models for response spectra, and these are within event residual models. At left is the Baker and Jayaram model from 2008, which was one of the earlier ones for crustal earthquakes developed from the NGA West data, and that was also updated by Baker and Bradley to 2016 for NGA West 2. In the middle is Carlton and Abrahamson comparing crustal versus subduction correlations in the dashed and solid. And then at right is a more recent one from Macedo and Liu for NGA sub. And the point of showing the three of these together here is that they're all really similar. And these are all for response spectra. So really the correlation models for response spectra don't depend too much on magnitude or distance or even tectonic category. So there's also models for the correlation for Fourier amplitude spectra, and that's what I've worked on more. There's also a model from Peter Stafford in 2017. So at left, I'm showing the Bayless and Abrahamson model, which has models for 4 residual components, and these are the between event residual, the between site residual, within site residual, and then the total correlation. And so these are from the NGA West 2 database for Fourier amplitude spectra, smoothed Fourier amplitude spectra. And these serve as the basis for some of the comparisons and the validations. So I've performed 2 evaluations of the simulations. Check how I'm doing on time here. Okay. Study 1 was for the SCEC broadband platform simulations, a suite of them. And study 2 was for Cybershake simulations, which are, of course, low frequency simulations. So study number 1, there were 5 simulation methods. These 5 use 1D Earth models and have no side effects. So they're all for a reference VS30 condition, and they're performed on the broadband platform. They include simulations of 9 crustal earthquakes. These are the same 9 that were used in the validation of the median by Goulet et al. And they each have 50 alternate source realizations. And then a 6th method that I include here was from Rogers et al. This was not on the Broadband platform, but it was evaluated at the same time. And that was for a magnitude 7 on the Hayward fault. And this one was a 3D model. So the procedure for this set of simulations was first to calculate residuals from the simulations relative to the FAS model, partition those residuals into components, as is done with ground motion modeling. First, the mean bias, the between event term, between site term, and within site. And then I've crossed out the between site term here because one of the drawbacks of this study was that we actually couldn't calculate a between site or partition of between site residual because these simulations are for 1D Earth model and for a reference VS30 condition. You can't separate the systematic site differences out. And then with those residuals, the mean bias, the between event and within site, calculate the interperiod correlation for each component and the total correlation. So here's an example of the results. These are, again, as I showed previously, the cross sections of the correlation coefficients. The solid are what was calculated from the simulations using this procedure. And then the dashed are those empirical correlations. And so, sorry, the 3 panels are the between event, within site, and the total correlation. What we concluded here was that none of the 6 simulation methods adequately capture the interperiod correlation over all frequencies. However, at the low frequencies, several of them are doing pretty well. Others are not. But we think that changes to the rupture generator are probably the most promising approach to modifying the long period correlations. And I have a slide on that in a little bit. And then also just a note, using the correlation of the FAS is advantageous because it provides simulation modelers or developers better feedback in terms of what to change. That's not as readily apparent when using the response spectra models. And so really, we find that more calibration is required. And so the second study is using Cybershake. The evaluation procedure was identical, although there were these key advantages. The Cybershake simulations are plentiful. And so that there's a much wider range of magnitudes, paths, rupture distances, site conditions, all those great things, so that we can select ground motions that much better mimic the NGA West 2 database. And that's good because it allows for our procedure of partitioning residuals and calculating the correlations to be an apples to apples comparison with the correlations that we're comparing against, which were developed from the NGA West 2. And much of that stems from the fact that the Cybershake simulations are for a 3D crustal model. So our conclusions from this study were pretty promising. Between 0.1 and 0.5 hertz, the Cybershake 15.4 version simulations have a satisfactory level of total interfrequency correlation. And so what I'm showing here is just one of those cross sections for the low frequencies. And the heavier blue fill and solid line are from the simulations. And then the lighter fill and the dashed line are the empirical. And so the fill areas here are the 95% confidence bounds. And the fact that these are not that these are overlapping means that there's not a statistically significant difference in the mean correlations. So that's the total correlation. We also did evaluate each component separately and found that the between site component of the residuals could be improved. And I think that this may be due to the relative simplicity of the seismic velocity model in the geotechnical layer in Cybershake. And so how site effects are being calculated, which is leading to too broad of amplifications of the between site terms and increasing the correlation. Or this could potentially be related to the effects of low frequency basin waves that are being mapped into the site terms. So these are both things to check into. So now that I've gone on to evaluation of some of the simulations, how can these be calibrated? So one way to sort of calibrate is a method that's proposed by Wang et al. And that's a pretty straightforward post-processing method. And so they've applied this to the San Diego State University simulations. Essentially what it does is it performs the complete simulation as normal. And then at the end, takes the Fourier transform of the time series and imposes the correlation on that Fourier spectra, and then does the inverse transform back to the time domain, and using the same phase angles. And so this works. The resulting Fourier spectra or response spectra have the correlation that's found in the data. The drawback to this is it sort of ignores the physical process of what might be causing that. So it has utility, but it does have that drawback. And so here I'm showing the correlations before and after performing that for San Diego State simulations. Another study from Song et al. More recently investigated the effect of pseudodynamic source models on the correlation using also the SCEC broadband platform, so 1D simulations, but with the Song et al. Source model approach. And so this study found that the cross correlation in source parameters, slip, rupture velocity, and peak slip velocity improved the between event ground motion correlation, but it was a very narrow frequency range where this improvement was observed in this sort of pilot study. We found that right around 0.5 hertz, the correlation for the between event component was improved. And so that's highlighted in the red and blue in this figure, that frequency range, where the red is after and the blue is before. But there was basically no effect at all other frequencies by including the correlation in source parameters. So that was a pretty interesting result, but one that should be studied further, I think. So my last slide here, okay, right on time. So part one, the importance of the interperiod correlation. Low correlation in the simulation underestimates the variability in the structural response. And this leads to fragilities which are too steep. They have an underestimated dispersion parameter, and then to non-conservative estimates of seismic risk if those simulations are being used in a seismic risk study. And then in evaluation of the simulations for these two studies that we did, the first, none of the SCEC methods evaluated were adequate over the whole frequency range, but some of them were acceptable at low frequencies where they're more deterministic. And for the Cybershake study, there was adequate total correlation between 0.1 and 0.5 hertz, which was very promising. The between site component should be studied further. My 3-year-old's knocking at the door. Sorry if you hear that. For the calibration of the simulations, it can be incorporated in a post-processing method if you're so inclined. In terms of a solution which doesn't ignore the physical process, work is very much ongoing still. This Song et al. Study showed that the correlation of source parameters may affect the between site component at a fairly narrow frequency range, but potentially there are others to explore. That's all I have. Thanks for your attention.